Hello and welcome to this lecture. So in the previous lecture we saw first order linear ODEs, and this was the general form of the first order linear ODEs, and we were looking at various examples that we saw all of them fit into it. So in this lecture we will see solution to the first order linear ODE. Some special case only we will see, but that's enough for us, and that itself is it's going to be a very interesting little way to solve these differential equations. Remember we saw that almost many phenomena are modeled by differential equations, and if you can solve them, you know exactly how processes are going to evolve, and all of that is very useful. So let's get started. Okay, so as usual, just like any other problem that we have taken up in this course, even the ODE solution, we'll start with the easy case. Okay, so this is the general form: f prime of x plus p of x f of x equals q of x. What is the easiest case in which I can solve it? I can solve it if p of x is equal to 0, right? So if p of x is equal to 0, all I have is f prime of x equals q of x. Now this is just an integration problem, right? Antiderivative problem. What's the antiderivative of q of x? That will be the answer to this question, right? Antiderivative of q of x plus some constant c, because the constant c can come in, and you use the initial conditions to find the c. Like you will know some value of f of x, you will know, right? Usually it's called the initial condition. So f of 0, for instance, you may know. So f of 0 is aq of 0 plus c. So that fixes the c, and so you can find f of x equals aq of x plus f of 0 minus aq of 0 or something like that, right? So that way you can find the c, and you can finish it off, right? So this is p of x equal to 0. Here's an example. Supposing f prime of x is sine omega naught t, then the solution is just the antiderivative, which is 1 by omega naught minus cos omega naught t plus c. So this is standard method. So p of x equal to 0 seems easy. Okay. So of course in real life you may not have p of x to be 0. So let's begin with a slightly simpler case where the constant case, where p of x is p, small p, some constant, some number. There is no dependence on x here. That's what I mean when I say constant. This is just a constant p. Okay. So the form I'm going to consider now is f prime of x plus p times f of x equals q of x. So what is always our method? We start with the easy case, and then we take a slightly more complicated case, but do something to reduce it to the easy case, right? So that's going to be the trick. So the trick is to see if we can convert this into the easy case. Okay. So if you stare at it for long enough, you'll see the left hand side looks like the derivative of a product, right? You have f prime and f adding to each other, right? It's sort of like a derivative of product, but the other term is a little bit complicated. So here is where this crucial trick comes in. You can multiply both sides of this equation by e power px. Notice this p is the constant number, some 2 or 3 or something like that. So I'm going to multiply both sides of this equation by e power px. Okay, this is a very carefully calibrated trick. It's a very carefully done, very nice trick. So you, instead of this equation, I'll try to solve this equation. E power px f prime of x plus p e power px f of x equals e power px q of x. Now e power px is not equal to 0, right? For no value of x is it 0. So this equation is equivalent to this equation. So okay, if you solve this, you solve this also. Okay. So now notice what happens to the left hand side by this simple trick of multiplying with e power px. Okay, so notice how all these new functions we learnt are entering the picture, right? The initial thing doesn't have any e power p in it, but then once I multiply by e power px, what happens to this guy? This guy has this fantastic form of just e power px times f of x, the whole thing derivative. Okay, this has this form, right? It's e power px into f prime of x plus p times e power px into f of x. So I've managed to convert an equation like this into an equation like this. Now this is something I know already, right? This is just the derivative of one function being equal to some other function, right? This I can do antiderivative. This I can solve with an antiderivative. So I've managed to convert a slightly harder case into my older case by multiplying with this e power px. This e power px is called the integrating factor. You multiply by a factor to make it into a simpler form. Okay. So once I have this form, I know how to solve this. E power px f of x is the antiderivative of e power px times q of x. So this is the antiderivative of this guy. Okay. So if I differentiate it, I'm going to get this. Okay. So of course I should be able to find the antiderivative of this. That's the problem, but this is just a standard problem, right? I'm going to find an antiderivative here. Okay. So that is the final solution. So now this is e power px into f of x. Now how do I get f of x from it? Multiply throughout by e power minus px, which I know is non-zero. So I'll get e power minus px, the antiderivative that I found here for e power px into q, plus c times e power minus px. So, this plus c, notice how crucial this plus c is that comes in the antiderivative. You got f of x to involve a c here. Okay. So, this is the cool little trick that helps us solve any ODE of this form. Okay. Any first order ODE with a constant p here, we can simply multiply by e power px and we are done. Okay. So, that's our solution method. We are going to start using it in our examples. We had these examples before. Let's start using it. First example is a falling object with air resistance, right? So, this was our equation, v prime of t plus k by m v of t equals g. If you remember, v is the velocity at time t, and there was the air resistance which was proportional to the velocity v and all that, and we wrote this equation. Now, in this equation, you can identify that small p is k by m, isn't it? And q of t is actually a constant g. Okay, this is just going back to identifying what it is. Instead of f of x, we have v of t, and then instead of p, we have k by m. Instead of q of x, we have g. Okay, that q of t is g. Okay, so both these things are constant. Take a look at it. That's a nice case, right? Special case. So in this case, what happens? What is e power pt times q of t? It's e power kt by m times g. Okay, can I find the antiderivative of this? Yes, of course I can. The antiderivative of this is just the same e power kt by m will come, then you have to multiply by m by k. So, that is the same as mg by k e power kt by m. If you do a differentiation of this, you will get this, right? If you take a derivative of this, you will get this guy, right? So, you can take a derivative and check, the k by m will multiply, it will cancel there, you will get back this. Okay. So, this is the antiderivative of this guy. Okay. Once I know the antiderivative of this guy, my solution is done, right? I can go back to my method. V of t is just this guy. This e power kt by m won't come here, mg by k plus c e power minus kt by m, right? The antiderivative gets multiplied by e power minus pt, isn't it? So, if it gets multiplied by e power minus pt, these two will cancel. So, you just get mg by k plus c e power minus kt by m. Now, how do I find the value for c, right? So, that is important. There you get using the initial condition. Some value of v of 0 I should know, right? V of t. So, for some t, I should know what v of t is. Usually people take v of 0, it can be any other value. Even if you know it for v of 1, you can substitute here and find c, right? That's what I am doing here. I know it for 0, so I put v of 0 equal to mg by k plus c equals 0. So, you get c equals minus mg by k. So, the point is one value of v, anywhere I know, I can figure out what the c is. Okay, so c is minus mg by k. So, you put these two together, you get v of t equals mg by k into 1 minus e power minus kt by m. Okay, see how easy it is. So, if you have the air resistance coefficient being k, acceleration due to gravity g, mass m, when it falls with mg by k into 1 minus e power minus kt by m. Okay, this is very, very interesting, right? So, what happens as t goes to infinity? When t becomes really, really large, this guy will go to 0. So, you get to a constant velocity mg by k. Now, this is the difference between with air resistance and without air resistance. Without air resistance, the velocity will keep on going, right? It will be just g times t, right? As you go down further and further, velocity will keep on increasing unbounded. But when you have air resistance, velocity will go to a constant, okay? So, let us see how quickly it goes to a constant. How do you plot this and see? But anyway, before that, let me quickly summarize. The idea is to identify the small p and the q of t, identify e power pt q of t, find the antiderivative, and then go back to the standard formula, antiderivative times e power minus pt plus c e power minus pt. And then you can't stop there, you have to find the value of c that you get by knowing one value of the actual function v, typically v of 0, right? So, this ball is falling from rest, so you know v of 0 is 0. It could be other values also, and then you get c also, and then plug it back in, you get the answer for v of t. So, this is the velocity for all time, and then you can study how this behaves. So, let us see a plot. A plot of this will really, really help us. So, I am going to plot v of t equals mg by k into 1 minus e power minus kt by m. I am writing it a bit differently. I am writing it as minus t by m by k. Okay, so this just helps me to visualize what is going to happen. So, notice this is how the plot behaves. It starts at 0, right? If you put t equals 0, you get 0, right? 1 minus 1, 0. And then when t goes really large, it goes to v infinity, and this 1 minus e power minus t will increase in this fashion. Okay, so e power minus t will decrease in this fashion, 1 minus that will increase in that fashion. Okay, so this is an important plot to remember. This 1 minus e power minus t into something is a very, very important plot to remember. It starts at 0 and keeps on increasing and goes flat like this. So, this final point is usually called the steady state value of the solution. When t goes really, really large, it goes to mg by k, right? When t becomes really large, it goes to a constant value. So this v of t keeps increasing and then it flattens out to a constant value as t becomes large. How quickly does it go there? How do I know how quickly it goes there? So that's where this notion, two notions will help you. V infinity is the value at infinite time, that's mg by k. The other one is a time constant. This is called the time constant. The factor multiplying t or dividing t is called the time constant. This is m by k. The reason is this m by k has the units of time actually. If you go back and look at how these things are defined, it has the units of time. And then at every m by k, you get closer and closer and closer to v infinity. And that is a good definition for amount of time you need to get to steady state. Okay. So if you look at m by k, m by 2, m by k, 3 m by k, 4 m by k, 5 m by k, you can see that after 1 m by k unit of time, you have reached v infinity into, so when t equals m by k, if you put t equals m by k, you are going to get 1 minus e power minus 1, right? V infinity into 1 minus e power minus 1. Okay, you are away from v infinity by some v infinity into e power minus 1. So that is something like 0.63 into v infinity. After 2 times the time constant, you've got to v infinity into 1 minus e power minus 2, and that's 0.86 v infinity. 3 times 0.95 v infinity, 4 times 0.98 v infinity, and 5 literally you're there. Okay. So usually in some 3 or 4 time constants, you will get to the steady state very, very fast. Okay. So this time constant measures how much time you're going to take to get to the steady state, right? So in 4 or 5 time constants or even 2 or 3 time constants, you will get to the steady state. Okay. So once again, this plot you should remember 1 minus e power minus t, this kind of plot will occur again and again in many systems and circuits that you may see as you go forward. Okay, so this is the first problem. Second problem is an RC circuit with a DC source, right? So you remember this thing, we had a 5-volt source connected through a switch to an R and a C, and we wanted to figure out what I of t will be as a function of time. And we derived this equation, I prime of t plus 1 by RC I of t equals 0, and this is my form, right? This is a standard form of the first order ODE. And what is my P? P is 1 by RC. What is my Q? Q is 0, right? So this is a really easy case. So e power pt times q of t is 0. So the antiderivative is also 0. So all that you have for I of t is c times e power minus t by RC. Okay, so c times e power minus pt. The antiderivative will go off to 0. It's very nice. How do I find c again? Again I put the initial condition. The initial condition here needs a little bit of thinking. I of 0, it turns out, is phi by r. The way I am imagining, the capacitor has no charge in the beginning, so all the voltage will fall across the resistance. So the initial current in the beginning, just at 0, will be phi by r. Okay, 0 plus basically. After that, it will start dropping actually, because I of t is this guy. So c is phi by r. So if you solve it, you get I of t is phi by r e power minus t by RC. Okay, so very simple expression for I of t. So I of t falls exponentially in t, right, e power minus t by RC, and the time constant is RC. Okay. So let's plot this and see, but once again I just want to remind you, for a DC source connected to RC with the time switch turning on at time 0, the current is going to fall exponentially. So what's going to happen as t becomes very large, when t goes to infinity, the current goes to 0, right? Current goes to 0, as in the voltage, the source is charging the capacitor. As the capacitor gets charged, the current here will drop, right? As you build up a voltage here, the current here is to keep dropping. It's going to drop exponentially, right? You may know it's dropped just physically, but how well it is dropping, you'll know only when you do the mathematics, right? So you see it's falling exponentially with a time constant RC, right? So that is something you see. So eventually what will happen when t goes to infinity, all the voltage 5 volt would have come across the capacitor, and the current will go off to 0. Okay, that's what you see here. Okay, so let's see a plot of this behavior. So this is the RC circuit with the DC source, and the plot of the solution, I of t is phi by r e power minus t by RC, and this will have an exponential fall like this, e power minus t, right? So I infinity is here, that is 0, and phi by r is the value at t equals 0. Okay, so I infinity is 0, and the time constant is RC, right? So this is the one value that's dividing t. In every time constant, I expect a big fall, right? So these are all plots of that, RC, 2RC, 3RC, 4RC, 5RC, at every time constant, 1 time constant, 2 time constant, like that. And then again, you can see at the first time constant, the value you have is I0 e power minus 1. I0 is phi by r. Okay, I0 e power minus 1, that's 0.37 I0. At 2RC, I have 0.13 I0, right, e power minus 2. 3RC 0.05 I0, 4 RC 0.02 and so on. Like by the time it comes to 5 RC, it is almost 0. Okay, so look at the way it's exponentially dropping down very quickly. The current is dropping down really quickly. Okay, so that's a plot of the solution for the RC circuit with a DC source. The next example is a little bit more complicated. We'll do that as part of the next module. Thank you very much.